Well, I'm back, guys. I'm on a I don't know how long a video. It shouldn't be too long. Kind of a two-part video. One part is to I've been an answer in the comments about a radio, and then the other part is a follow-up on the iTube. Anyway, on the first part here, basically the problem is that even with doing some wiring changes and stuff and a few other things, when the radio is switched off, it still has a hot chassis, which is rather interesting, considering the chassis itself is actually a floating chassis. It shouldn't be hot. That being said, there is, and which I'll get into in a minute, there is one way that it can be, or at least seem to be. Now, the first thing I want to make sure of is, as far as actual wiring and connections and stuff, this is a Philco 481256, by the way, and it has a phono and stuff. But the way the factory wired it, they got the switch here, which this would be actually considered ground, if you will. This is more like considered the hot. If you put a polarized plug on, this would be the hot side and this would be the neutral side, but that switch needs to be rewired so that this side is what's being switched and this side stays on, so that the neutral will always be neutral, and that'll be the only thing that's actually connected when the switch is off. Now, that being said, there is a potential, just the way it's wired with the lamp here, and being it's AC, so capacitors matters not. There are, when you have a floating chassis, you can't have it completely floating. If you do, you'll end up with a, well, you end up with the chassis being kind of like an antenna, and then through capacitance coupling and even inductive coupling, it starts transferring various interference signals, both inside the radio, as far as from one part of the radio to the other part, but also outside the radio. When it sees no ground whatsoever, then it is literally nothing but a big antenna. So any outside noise, there is absolutely no shielding due to the chassis. So in order to fix that, what they do is they'll add in some circuits and filters, basically. And one is this one right here, this little it's a capacitor inductor combo. This is one of those capacitors where inductors where if you ever looked at well, Philco is notorious for them, but some other radios, and I showed some of these, but it's where they take the capacitor and then they wrap some wire around it, connect to one end of the wire to the capacitor, and the other end goes to ground, and of course the other end of the capacitor will hook into the negative or DC ground. So that's what this thing is. Sometimes, if this capacitor is not replaced, it can either badly leak or short, and in that case the chassis then will be actually effectively connected to ground. The other point that they use is a resistor down here. Now generally resistors go up in value, but they can short sometimes, so this is something else to check. And then of course some of the other problems that you can have is your wiring itself, or things of this nature. You could have actually a wire coming in from the plug or whatever, going to the rectifier or some point along through this hot lead that could very well have bad insulation on it or something, and could be effectively kind of shortened to the chassis. Although when the thing's on, it should still be hot. So the thing, well, two things I would do. One, I would check out this and make sure that if you haven't replaced the cap, replace it. You can just rewrap the wire. You can either stuff the cap or put the cap, a new cap, right kind of parallel to it, except disconnected. But you could, you know, leave it kind of basically one end still hooked to this inductor. Or you can unwrap this and wrap it around the new cap. It's not critical per se on its coil size and stuff. Either way, this would be one possible culprit or problem. The other problem is this resistor. Check it, make sure it's alright. And the other thing is make sure that the switch is in this side, the side that's going to the rectifier tube, to pin 2 and pin 4. That should be where your on and off switch should be actually, and then this side would be just directly connected. Now, what else could happen? How could you get a hot chassis and everything is basically correct or seemingly correct? Well, except for maybe the switch is not switching off the hot. Well, you got to realize that these meters have a 10 megohm input impedance, and VTVM generally runs on DC, will run 11. AC, it's a little lower, so a VTVM would load the circuit. But a digital meter like this is 10 megohms, whether it's AC or DC. So that means not very much current's ever going to go through it. It's not going to see much current. So you could effectively actually have a chassis that should be floating and maybe not have the switch, the hot side on a polarized plug. You know, maybe it's not switching it off. You know, it's still hooked up the way they generally hooked them up. You could still actually read voltage off that chassis. And the reason for that is, you know, even with the switch off and this is still connected to hot, there are paths for it to get through this resistor and even that capacitor if it wanted to, but it can get through to the chassis in an extremely small current situation. In other words, not much current. Now once it starts, you know, you would try to load it down. Once you start pulling current off of it, through it, then this resistor would start getting enough voltage drop that across it that it would actually pretty well block any voltage coming through. Plus the capacitors would start trying to charge, and that would start slowing the process down. And you would then, it would not show any real voltage there anymore. The way to test this theory is real simple. Get you like you want a fairly heavy load, so you want like a 40 watt light bulb or a 20 watt light bulb or some sort of light that's, you know, 120 volt, and just rig it up. You can put it in a socket, or you can just solder some wires onto it, however you want to. Connect one side to the chassis and the other side to ground, to your ground post here. If this chassis is truly hot, then that light bulb will light. If it's not, the light bulb won't light. And even though the meter may be showing that there is something there, the light bulb won't light. And actually, if you leave that hooked up and you check it then with the meter, the meter won't show much. So just some quick observations on it and stuff. But the main thing is, if you got to put a polarized plug on, this would be your hot side. Put the switch in this side and then this side would be your neutral, which will be then continuously connected. Now, one last little thing. I talked about this before and showed a little deal on it, so there's a recent video on it, but checking the house wiring. But you can also check it another way. This wide plug right here, this is neutral. This should be at the same potential as this right here. This is your ground. This is the hot lead. If you take your meter, set it on AC, and you put one prong in here and one prong in here, it should read 0. If you do not, then part of your problem could be just simply nothing more than your house wiring is not right. So that's another thing to check. So anyway, give it a try. Do some of the points, check some of the things I've talked about. Make sure that this is your hot lead and it's switched. And if you're still having any troubles, or you've already done all this or whatever, try the light bulb trick and also check your outlet. So anyway, with that being said, I think that's about all I got on that. Now, for the follow-up on the iTube, I'm going to get this set up so that I can use both hands. And let's see if I can get it turned down here a little bit, so I can kind of see what I'm doing and you can see what I'm doing. So basically what I did was I cut all the leads. There's what's left of the filament right here. And I wanted to show how this thing kind of fits together. Now here's your target, the part that turns color green on you. It is connected through to this back plate, which that back plate then is it used to set on here like this and went through these holes. This is mica, so it's insulator. Those holes had these leads that came up through, so this actually connected to these leads here, and one lead had the getter on it, getter target, and then the other lead, and both of them went into the glass, but I can't remember which side actually makes connection down through inside here and goes down to the pin, but one of them goes to the pin. Now this here, well, first here's your cathode. Alright, that's all there is to a cathode right there, and you won't be able to see it, but there's what remains of the heater is still inside it. And the cathode would extend up through, well, actually goes this way, through the grid and stick down just a little bit down here in the bottom. It also extended on up through the top here, if I can get it through there, which I probably can't. But anyway, it comes up through the top about that height, and the electrons come from it, coming out, and hits this target, which then turns it green. Now the grid is only for the triode. Okay, see, that's all further it fits down. That grid is only inside this part. This is the plate of the triode. The other grid that's shown on the schematic drawing of the tube is nothing more than this little piece of metal right here. That's what shadows out when they get that voltage difference. This becomes appearing negative compared to this, the target plate. Then that's what creates your shadow, because it starts blocking the electrons that are trying to come off that cathode, excuse me, in that area. So that, this is sitting down like this, the cathode comes up through there, and it starts deflecting the electrons when it is a different potential than this plate here, the target plate. So this plate is hooked to B+, then through a resistor, the 1 meg, or if you're running low voltage, 500K, but either way, that resistor then is connected to this plate, which is connected to this. When there's the same potential, you get a full green. When they're at their maximum difference potential, in other words, when this is at cutoff, then this is max. It has basically 0 volts on it, so it appears the most negative respect to this one. And well, actually it's reverse. When it's at its max, it would be when it's drawing the most current. So when you got the grid at 0, this draws the most current. But in any case, when that voltage is at the maximum difference, that's when you'll get your 90-degree reflection shadow. Anywhere in between then is different angles of degrees. But that's how how it's all related. The grid here is connected to the signal, the AVC, and as it approaches cutoff, then it basically is shutting off the current in this, so then there's no drop across the resistor, and then it's 0 angle. When this is at 0, say, at its lowest voltage, then there's a maximum current flow through the tube, through the triode, which then makes the maximum difference in voltage between this plate and this plate, which then makes this the most negative in respect to this plate and deflects the most electrons. So I wanted to show how that's all connected. This connects directly to here. All the grid is just down inside here, which is inside the triode plate. It does not extend up above. And I don't know if you can see this, but I'll kind of show you what is truly the difference between the 6U5 G5, because they're both the same tube, and the 6E5 is well, let's see here. Let me get something here to kind of backdrop it a little bit. Is right here. You see how these windings are separated some? They get closer and closer together at the top and the bottom, but they start spreading apart and get really spread here. Well, that is known as variable mu tube or remote cutoff. And basically the 6U5 has that, the 6E5 does not. And what that does and changes is that angle that I showed on the graph, how the angle changes with voltage on the grid here, and how it changes the opening angle from close to maximum opening. It had a good sweep in it, made a nice curve, extended out a ways at maximum voltage. Well, the 6E5 would be what is known as sharp cutoff. They're evenly spaced, so it'll be more linear, more straight line. It still has some curve, but it'll be more straight line, so that it goes pretty linear from fully closed to fully open, where this one is more logarithmic in the way it works. So that's basically all I got on the I-tube. They're really they are a simple tube, but I wanted to show you how how all the parts interact and how they connect. And of course, you got the top cap here, which is nothing more than just blocking out the light from the filament, so you don't see it. So I hope that helps, and I hope I explained that well enough. So if you have any questions, just leave the comments and leave them in the comments, and if it's going to take more than a couple sentences to answer them, I'll just make another video. So until next time, thanks for watching.